Hi folks, today we are going to take a look at a clock built around the TMS1943. First, I want to point out that this IC exists in two different 40-pin DIP packages. The TMS1943NL uses the standard 2.54mm pin spacing, while the TMS1943N2L uses a narrower 1.78mm spacing. This clock is very similar to other designs from the same period, using devices such as the LM8361, the S1998, and the MM5387, all of which are already part of our collection of videos. Unfortunately, I was unable to find a complete datasheet for this IC. However, I did find several images scattered around the web, and there are two in particular that I would like to highlight. The first image shows the schematic of a clock built around our IC. I want you to pay close attention to the way the pins are numbered. The numbering initially follows the normal sequence, 1, 2, 3, up to 10. But from there, some numbers are skipped, giving us 12, 14, up to 21, then 23, 25, and so on. I strongly recommend being especially careful with pins 28 and 29, because these are the power supply pins. With this unusual numbering convention, it is very easy to make a mistake. There is also something even more important to be aware of. The circuit appears to have a direct connection to the main supply, probably intended to control other external devices. So extreme caution is required when working with this type of circuit. Now let's look at the second image. This one contains something particularly interesting. For those of you who regularly follow this channel, this will probably not be a surprise, but it is still worth emphasizing. Look carefully at the labels used for the power supply pins. Pin 28 is marked VSS positive, and pin 29 is marked VDD ground. At first glance, this may appear completely backwards, but it is not an error. We are dealing with an early LSE integrated circuit from the PMOS family, and at the time, this power supply notation was commonly used with this technology. Because this is such an important detail, I want to emphasize it once again. If you encounter one of these old integrated circuits, and you are unsure about the correct power supply polarity, especially when you do not have the original schematic, look carefully at the polarity of the electrolytic capacitor on the PCB. You can also examine the orientation of any rectifier diodes present on the board or in the circuit diagram. These clues can help you determine the actual polarity of the power supply. Instead of relying only on modern assumptions about the VDD and VSS labels, you may also notice that the two central dots on the clock are not blinking. Normally, a 1 Hz output would be used for this purpose. However, in this particular design, that output is instead used to construct the segments of the tens digit of the hour display. Judging by the information available in the reference book, there also appears to be a version of this integrated circuit design for use with an LED display. The version we are showing here, however, is intended for a VFD. In one of our previous videos about the S1998, we demonstrated this difference. Now let's take a closer look at the VFD itself. This is a Futaba display, with the reference 5LT02/02M. It is clearly an older display design. One easy way to recognize this is the sealing tip protruding from the rear of the tube. With this manufacturing method, the rear glass was perforated during production, and the tube was later sealed by melting the glass around this evacuation point. Another very important characteristic of this VFD is that every segment is independently accessible. The display uses only a single grid, with all of the individual segments available through external connections. This is possible because this type of clock does not use multiplexing. In our demonstration, a potentiometer is used to adjust the brightness of the segments. The VFD also includes AM and PM indicators. However, because this clock is configured to operate in 24-hour mode, those indicators are not used. Looking now at the PCB, we find an
H9013
transistor. This appears to be used to control an external alarm device, or possibly the sleep timer function. The presence of a switch in this part of the circuit suggests that the output could have been used, either to activate the buzzer or to control the radio itself. The 50 or 60 Hz reference signal is obtained directly from the transformer. It passes through a 100 kΩ resistor, connected to one side of a 7.5 volt AC secondary winding. A second transformer secondary is also available, providing 2 times 7.5 volts AC. This supply is intended for the peripheral circuitry, such as the radio or the buzzer. Clock adjustment and control are handled through 5 keys. These are very simple mechanical contacts, made from metal springs that press against a metal bar. That bar is connected to the positive supply potential. And that is essentially what we need to understand this clock. For those of you lucky enough to come across a TMS1943, I hope these observations will help you identify the circuit correctly, understand some of the unusual design choices of this early technology, and most importantly, preserve the original hardware and bring one of these old clocks back to life.